This first problem, the first task you were given to do is to factor by grouping, factor using the AC method, 12x squared minus 5x minus 2. And so the first question I have is, what was the sum and product game that you played in order to get the AC method started in this factorization? What did you need the sum of the two numbers you're looking for to be? The sum is always the middle term, the middle coefficient. The sum is -5. And what did the product need to be? I need my numbers to add to -5 and multiply to give me, 24, also with a negative sign in front of the 24. That's where the AC method gets its name, right? Multiply the A coefficient times the C coefficient. That's what the product needs to be. So two numbers which multiply together to give me -24 and which add together to give me -5. What pair of numbers did you find that fit that bill? 3 and -8. They multiply together to give me -24. They add together to give me -5. Great. So then we use that 3 and that -8 to split apart the middle term. So +3, and -8. That's where my x's are going to come from. And now that my grid is filled out, I just have to fill out the outside. I can get that process started by factoring one of my rows, finding the GCF. What's the greatest common factor of 12x squared and 3x? So they both have an x, and they both have a 3. So 3x is the greatest common factor. 3x times what is going to give me 12x squared? There's a 4 there, and there's also an x there. Don't forget that x. And then 3x times what is going to give me 3x? That's just 1. And then my last square, 1 times what is going to give me -2? -2. And so that's where my factorization comes from when I use the AC method on this. 4x plus 1, 3x minus 2. Okay, great. So once we've used the AC method to discover that factorization, my secondary question was, how do we then solve this quadratic equation for x? If I can replace 12x squared minus 5x minus 2 with this factored expression, what does that allow me to do now that I wasn't able to do before? Where do I go from here? I have a factored expression on the left side of an equation, and I have a magic 0 on the other side of the equation. So now what? This is a step everybody forgets. But it's the entire reason that we factor, is it allows us to solve equations in this fashion.
We have to rewrite
The entire point of factoring is that it then allows us to say, if I multiply two things together and give me 0, that must mean that one of the original things must have itself been 0. It's the zero factor property. So when the left side is factored and the right side is 0, it means I can split my two equations. I can split my one complicated equation into two simpler equations. 4x plus 1 is equal to 0, and 3x minus 2 is equal to 0. And now I have two much simpler equations that we can solve just by reversing the order of operations. Subtracting 1 from both sides, and then dividing by 4 to get as my first solution x equals -1/4. So that's also something new that we see in these examples, is that sometimes the solutions are not whole numbers, they're not integers. Right? In this example, my solution was a fraction, -1/4. And then a similar thing is also going to happen when I solve the 3x minus 2 is equal to 0 equation, adding 2 to both sides. 3x equals 2. And then dividing both sides by 3, x is equal to 2/3. So this particular quadratic equation ended up having two solutions which were neither one of them integers. Right? Both of my solutions were fractional, -1/4 and +2/3. So problem 2 asks us to factor 25 minus 36w squared. And this is an expression that looks considerably different than the ones that we've previously tried to factor. So there's something to notice about this expression that should help us in the process of factoring. And what we notice is that both 25 and 36 have what nice property? What kinds of numbers are they? The way we could approach this problem is to think of the 25 and the 36 as my A and C. And if I did that, then I would be looking for a pair of numbers which multiply together to give me A times C, which add together to give me the middle term. Okay, well, what's the middle term? What are these two numbers going to have to add together to give me? It would be the coefficient of w to the first power. But there is no w to the first power. So what does the sum need to be? Zero. Okay. So my two numbers need to add together to give me 0. They also need to multiply together to give me 25 times 36. Wow, it's kind of a big number. I think it's 900. I think I have that right? No, yeah, I have. All right, so they need to multiply together to give me 900. Sorry, negative 900. I don't want to lose that negative sign in front of the 36. So they multiply together to give me negative 900, and they also add together to give me 0. Now, the fact that they add together to give me 0 tells me what about these two numbers? What kinds of numbers add together to give me a 0 sum? Those two numbers have to be equal and opposite. If they add together to give me 0, one of them has to be positive something, and the other has to be negative that same thing, right? Positive 6 and negative 6, positive 12 and negative 12, positive 8 and negative 8, positive pi and negative pi. I need a pair which are positive and negative versions of the same thing, but which multiply together to give me 900, negative 900. But it has to be the same number. What number multiplies by itself to give me 900? 30. So in other words, if we approach this with the AC method, then the numbers that are going to win my sum and product game are negative 30 and positive 30. And then filling in my cross terms here, I'll get a negative 30w up there. I'll get a positive 30w down here. Now all we have to do is fill out the outside of this grid. And just to economize some time, let me condense this step here. We're going to find the greatest common factor of 25 and negative 30w, and that greatest common factor is 5. And then 5 times 5 is going to give me 25. 5 times negative 6w is going to give me negative 30w. And then between this negative 6w and this negative 36w squared, or equivalently, between this 5 and this 30w, we see that the missing factor here is plus 6w. And that accounts for our answer. So it turns out that the AC method is kind of a multi-tool. Right? I'll be honest, I didn't think about using AC method for this problem, but it works. All we have to do is be extra careful that we don't miss that the middle term, the missing middle term here, has this coefficient of 0. So the AC method definitely got us to where we wanted to be. It's not the method that the authors of our textbook would likely have recommended. So just to get this on the table, the property that I was hinting at in the beginning, that 25 and 36 both share, is when you look at this factorization, you notice that when this 25 factored, it factored into a product of a number with itself, 5 and 5. Similarly with this 36, when it factored into a product of a number with itself also, 6 and 6. So both of these coefficients were perfect squares, the square of 5 and the square of 6. And that accounts for why, when we do this factorization, we get the same number for each of these two factors. And so a lot of textbook authors will spin this as a special kind of factoring, that if you notice that these are perfect squares ahead of time, you can use that observation to give you sort of this cookbook way to factor it. But if you get a lot of practice applying the AC method, the methods of our course, it works here too. So I kind of like that. So for the last problem that you had to factor here, 10y to the 5th plus 26y to the 4th minus 12y to the 3rd power. What made this different? Why was this a different kind of factoring problem than the ones that we've tackled before? what looks different about this expression? All three of the terms in this expression, they all have factors of y in them. In fact, a lot of factors of y in them, right? The minimal amount that we have is 3 factors of y in that lowest order term, and then there's 4 here and 5 here. In all the examples that we've done before, the powers of our variable decreased from 2 to 1 to 0. In this example, it's 5 to 4 to 3. So we have a lot of extra y's floating around. So how do we approach that? Before we think about the sum and the product game, what's the first move in our factoring strategy? Common factor. First thing we should think about is see if there is a common factor that we can take out of all three of these terms, that all three of these terms have in common. Well, what do 10, 26, and 12 all share in common for their greatest common factor? 2. And if I take out that 2, I'm going to get a 5 here. I'm going to get a 13 here. I'm going to get minus 6 over there. That accounts for the coefficients. Then how many factors of y do these three share in common? How many factors of y can all three of those terms agree upon? 3 factors of y. Y to the third. Right. And when I take out the y to the third from my y to the fifth, how many y's are going to be left over? 2 of them. Again, dividing powers, y to the fifth divided by y to the third, I subtract the exponents. Y to the 5 minus 3. Same thing with my middle term. Y to the 4 minus 3 is y to the 1. I'm not going to write the 1. And my last term, all of my y's have been taken out, and so I just get a constant. So that's the first step in the factorization of this polynomial, is we take out that greatest common factor. And then we focus the rest of our energy on factoring this cofactor that's in parentheses, 5y squared plus 13y minus 6. And that then becomes the AC method case, where I'm just going to abbreviate this part. We play the sum and the product game, looking for a pair of numbers which add together to give me 13, and which multiply together to give me negative 30. That's where my A times C goes in this example. And the pair of numbers which win at this game are positive 15 and negative 2. I believe I have that right. And so that tells me then that I can split my middle term into plus 15y minus 2y. And then all I have to do is take out the greatest common factor of one of my rows. And here that greatest common factor will be 5y. Cofactors being y and 3. And then 3 missing factor negative 6 gives me a minus 2 from there. And then that finishes my factorization. One of the hardest things to remember often is to keep carrying through your 2y to the third. Sometimes in all of the hubbub of doing the AC factorization, you forget that GCF that you brought out at the very beginning of the problem. But it's still there, and so it should be a part of your answer too.